Welcome my friends, welcome to my next lecture. Now in my last lecture I was discussed about Cauchy-Goursat theorem. In fact I talked about many things like if like the existence of what is called antiderivative or primitive, and then path independency of contour integrations and Cauchy-Goursat theorem. So if you remember, there is a theorem, the following conditions are equivalent, like if I start with my functions f, which is analytic in a simply connected domain, and if I take any 2 points inside the domain, say z0 and z1, then whatever contour I can take starting from z0 ending at z1, the corresponding contour integrations is independent of choice of the contour. Then f has a primitive, and then if I take any simple closed contour, then the contour integrations is 0. So all three things are equivalent. So that's all about the Cauchy's theorem or Cauchy-Goursat theorem for simply connected domain. Now today's lecture I will talk about Cauchy's theorem in multiply connected domain. That means if I have a domain and suppose there is a hole inside, that means it is not simply connected, then what can I say, or what will be the kind of corresponding statement of Cauchy-Goursat theorem or say Cauchy's theorem for multiply connected domain. So that's my plan for today's lecture, and then if time permits, then I'll start with another beautiful theorem that is called Cauchy's integral formula. Okay, so this is a kind of again it's very nice applications of Cauchy's theorem. So let me just start with Cauchy's theorem or Cauchy-Goursat theorem for multiply connected domain. Okay, so as I said, so this is the theorem, you kind of can just recall it. So this is combinations of whatever observations I have discussed in my earlier lectures. So it says that if I start with the continuous functions on a simply connected domain, then the following three statements are equivalent. What are the statements? First of all, so the integrals of f along any contours lying entirely in D extending from the point z1 to z2 all have the same value, that means independent of the choice of the contour. F has an antiderivative, and my functions, if I take any simple closed contour inside my domain, then the integral of f along this contour it's actually 0. Okay, so it is a combination of everything. Now, so as I said, so now I will have what is called my, I want to talk about the kind of Cauchy's theorem for multiply connected domain. That means now look, this is my domain. So so green one is the domain. That means you have a domain, but there is a hole. So then what will be the corresponding statement of Cauchy's theorem in a multiply connected domain? So first concept will come is the deformation of contours. What is that? So it says that if I take two simple closed positively oriented contours, so let C1 and C2 be two simple closed positively oriented contours such that C1 lies interior to C2. Now what does it mean? The meaning is that, so C2 is the contour, right? Simple closed contour. So what is the interior? Interior is, this is the domain interior, right? But the white portions will not be there because white portion is not a part of the domain. But I am considering my another contour C1, which is nothing but this one. You see, it is stays in the blue line, blue region. That means it is actually the interior region bounded by C2. That's exactly I have written. So C1 and C2, two simple closed positively oriented contours such that C1 lies interior to C2. Because of the picture, it is clearly it clears. Now then, what I am saying is that if f is analytic in a domain D, my domain is D, that means only the green region, and the green region is multiply connected because there is a hole, because white portion is, this portion is not a part of the domain, it's white one. So therefore if f is analytic in my domain, then it says that analytic in domain that contains both C1 and C2, like because it's C1 also in the blue region and C2 also is in the blue region, okay, that contains both C1 and C2 and the region between them. Of course the region in between, this is the one, also it is a part of the domain D. Then the conclusion is that the contour integrations over C1 is same as contour integrations over C2. So that means the value of the contour integrations over the larger contour C2 and the contour integrations of my f over the smaller contour C1, which is lies interior to C2, both value will be same. So that is called the deformation of contours. So that means if I have a large contour, then I can deform it and make a smaller contour C1, which is lies interior to the region C1. That's what the kind of statement. C1 and C2, two simple closed positively oriented contours such that C1 lies interior to C2. That means if this is my C2, this is the interior region, that is the blue one, and C1 is sitting inside, that means this is my C1. Okay, so that is the meaning of that the contour C1 lies interior to C2. Then the kind of conclusion is that if I start with my functions f, which is analytic in the multiply connected domain D, which contains both my contour C1 and C2, then the contour integrations over C1 is exactly equal to the contour integrations over C2. So that is called deformation of contour. That means I can deform my contour to the smaller contour. So that means even if I consider this kind of contour, so if I let it be C3, then integrations over C2 is same as integration over C1 is same as integration over C3. Same thing, you can have it. So that means I can deform my contour, okay? But it should satisfy all the properties. That means contour C1 and C2 should lies in my domain D, and the deformation contour, that means C1 is the deformation of C2, you can think in that direction. C1 should lies interior to C2. If these things happen, this is the corresponding what is called contour integrations or line integral will be the same value. Now how to do that? So I can prove this theorem again using what is called Cauchy-Goursat theorem. That means somehow I break my domain into two parts, and each part will be what is called simply connected, and in simply connected domain, you know, if I have a simple closed contour, then by Cauchy's theorem or Cauchy-Goursat theorem, the corresponding what is called contour integration or line integral will be 0, and then I will have to combine these two things. So that's how I will do that. Now pictorially you can do that. So because this is a kind of multiply connected region, then what I will do somehow, suppose if you can think about in this way, suppose this is your like region, okay, so this is my region, right? This is multiply connected region because this is a like you can think about this is a plane, complex part of the complex plane, and there is a hole inside, right? So therefore this kind of region is multiply connected region, and what we'll have, you will have some contour here, okay, and some smaller deformation of contour here. But I want to conclude that the integrations over the larger contour will be same as the integrations over the smaller contour. What I will do, so I will somehow cut this region into two parts, and each part will be simply connected, and I will apply Cauchy's theorem. But if I have this kind of domain, how to make it or how to cut this domain into two parts so that each domain will be simply connected, and that you can easily do that. What you will do, you just kind of if you have a scissor, then you can just use a scissor and just cut it, okay? Then now this domain you can make it two parts, right? Now look, this is the lower one. Now lower one, you see there is no hole because this is the region. So this is the region, right? Because there is no hole. So this region is simply connected, okay? And there, if I have the contour, part of the contour will be there. So what I will do, so this is one portion of the larger contour, and this is the smaller portion of the or it's called deformation contour. Then what I will do, I just cut through the scissor. Then I'll draw a line from here to here and make a simple closed contour. Like I'll start from here, I'll go there, then come back here, then I'll go there, and then I'll come back here. So then it will be a simple closed contour in this simply connected domain, and there I can apply what is called Cauchy's theorem. Then I'll have to say that I'll conclude that my corresponding contour integrations will be 0. Similarly, this is one part, this is the lower part, and above part is this one. This is also simply connected, right? So this is also simply connected because you will have this kind of domain, because there is, I know there is a kind of curve is there, but there is no hole here. So this is also simply connected. So now there also it contains the part of the contour, right? This is the bigger contour, okay, and this is the smaller contour. Then what I'll do, I'll draw a just line here. Then what I'll do, I'll start from here, okay, then I'll take the larger contour, then I'll come back here, again I'll have a straight line, then I'll come back to the smaller deformation contour and come back here. So therefore I'll have a what is called simple closed contour in this domain. This is simply connected. Again I will apply Cauchy's theorem, then the corresponding contour integrations will be 0, and then what I will do, I will just add these two things, and then I will have the corresponding theorem. So that's the target for this deformation of contour. So that means if I have a multiply connected domain, the idea is that you just break your multiply connected domain into two parts. Each part will be simply connected. There you apply what is called Cauchy's theorem or Cauchy-Goursat theorem. Okay, so that's what, see, I have done it. So this is the proof, deformation of contours. It says that. So look, so this is, as I said just now, I saw through the papers. So what I have done, I just introduce a lines, say L1 and L2, so that, so this is the portion, upper portion, this is the upper portions, where this is a simply connected domain, and this is the lower portion, that the blue region, this is another simply connected domain. So this is multiply connected because inside the white one it is not a part of the domain, because the blue region is the multiply connected, but here look, there is no hole in the blue part here. This is simply connected, as well as this blue region is also simply connected, and there I will introduce two lines L1 and L2 and to make a simple closed contour. So this is my simple closed contour, and there I will apply what is called Cauchy-Goursat theorem. So that's the idea. So what I am saying is that assume that both C1 and C2 have positive counterclockwise, so that's kind of without loss of generality I am assuming. So C1 and C2, I am considering two contours, both are positively oriented. Now we construct two disjoint contours or cuts. I will introduce two cuts like L1 and L2 that join C1 to C2. The contour C1 is the cut into two contours C1 star and C1 double star. That means if I introduce a line, so that for example earlier what we will have, this is C1 and this is C2. So what I will do, so I will introduce a line L1 and this is actually L2. Now if I introduce this line L1, that means this L1 it cuts, L1 and L2 cuts my contour C2 into two parts. One is this one, another is this one. Similarly, this L1, L2 cuts C1 into two parts. One is this one, another is this one. So that's exactly I have done it. So that's what I have written. So the contour C1, which is nothing but, this is my contour C1 contour, okay. It says that the contour C1 cut into two contours C1 star and C1 double star. C1 star I am considering the upper half, upper part, and C1 double star is in the lower part. Similarly, C2, because of this introducing the cuts L1 and L2, it also break my contour C2 into two parts. One is C2 star, another is C2 double star, okay. So then now what we'll have, now I will have so what I have done, I have introduced two cuts using L1 and L2, then I break my multiply connected domain into two parts and each part is simply connected. And there somehow if I say that look, this is a simple closed contour, then I will apply that yes, by Cauchy-Goursat theorem my corresponding contour integration will be 0. Now if I have L1 and L2, now look, suppose this is my L1 and suppose this is my L2. So this is the way. So you can think about, so L1 is this one and L2 is this one. So look at the orientation, I am using this way, okay, you do not, so that means if I just remove it, then it will be clear which direction. So I am taking, so I am considering L1 in this is L1, and what is my L2? L2 I am saying that okay, L2 is in this. That's how. So it doesn't matter. You can have different directions as well. So but you need just like think about a scissor and you cut L1 or introduce the line L1 and L2 and cut those contour into two parts. That's it. Okay. So now in this simply connected region, so my aim is to apply Cauchy's theorem. That means I have to somehow give a simple closed contour and then I will conclude that, or I can say that look, this is my simple closed contour and there my contour integration is 0. Now what I am doing is that now consider this contour K1. What is K1? Look, so it says that you start minus C1 star. Now look, so what is C1? So C1 I have two parts. One is C1 star and another is C1 double star. Similarly, C2 will have two parts. One is C1 star, one is C2 star, and another is C2 double star. So what I am doing is that I am saying that you start K1. K1 is minus of C1 star. Now so what is C1 star? C1 star actually it's going from there to there. So what is minus C1 star? It should be in the opposite directions. Okay. So okay, I just look. So this is okay, this is C1 star is the kind of different one. Okay. So now, so okay, so what is minus C1 star? So minus C1 star, okay, let me just check. What is C1 star? Yeah. So, yeah. Okay. So I have a cut here, I have a cut here. So C1 is the anti-clockwise direction. So that means this is the portion C1 star and this is the portion C1 double star. Now, that means by default, since C1 is positively oriented, so C1 star will also be positively oriented because this is the portion C1 star. But then what is minus of C1 star? This should be opposite direction. That means it will be negatively oriented. That means it should be what is called clockwise direction. So C1 star is anti-clockwise directions, minus C1 star is the clockwise directions, and that's exactly this. So minus C1 star, that means you should start from here, you come here, then you have L1, so L1 is this directions already there, you come back here, then C2 star, it is automatically positively oriented, you come back here, and then you have minus L2. See, L2 is in this direction, so minus L2 means in the opposite direction there. So I am starting from here, I am going via minus C1 star here, then I am taking L1, I am coming here, then I am taking part of C2, that means C2 star, I am coming here, and then at the end I am come back here. So from where I am started, again at the same point I reached using this contour K1. So K1 means what? It's a simple closed contour starting from this point, and this is the way you can. So first you take minus C1 star, reach here, then take L1, reach here, then take C2 star, reach here, and then take minus of L2, come back to the same point. So therefore this contour K1, which is simple closed contour staying fully on the blue shaded region, which is simply connected. There is no hole. Now you can apply Cauchy's theorem, and you can say that yes, if I apply Cauchy's theorem or Cauchy-Goursat theorem, integrations over K1 will be 0. The same trick you should do in the region, in the blue shaded region, in the lower part as well. This time what contour I am considering? K2. K2 is a minus C1 double star. So that means, so what is C1 double star? Look, come back here. So this is C1 star, C1 double star. C1 double star, that means it is going in this direction. That means what is called anti-clockwise direction. So therefore what is minus C1 double star? That means it should be in the what is called clockwise directions. So therefore minus C1 double star, that means I should move in these directions, right? Anti-clockwise. So because C1 double star is in the clockwise directions, right? This is C1 double star. This is I'm in the what is called clockwise directions, I'm moving. So therefore minus C1 double star, it should be in the opposite. So that means I'm starting from here, using minus C1 double star, I am reaching here, okay? That is okay. Then I am considering L2, that means through L2 I am reaching here. Then I am considering C2 double star. C2 double stars, this is again in these directions, so I will reach up to that point, and then I am having minus of L1. What is L1? L1 is in these directions, minus of L1 means opposite directions, I am reaching here. So then I am starting from here, I am taking minus C1 double star, reaching here, then I am taking L2, I will reach here, then again I am taking C2 double star, I will reach here, and by taking minus of L1, I am come back to the same point where I started. So again this contour K2, it is a simple closed contour sitting fully in the blue shaded region, which is simply connected. Now you apply Cauchy's theorem, so that's what exactly I have written. The functions f will be analytic on a simply connected domain D1 and D2. So this is part of D, which is D1 and D2, because f is analytic on D, which is D1 and D2 is sitting inside D. So therefore f is analytic on the domain D1 and D2 containing K1 and K2, because this is D1 is the blue shaded region where the simple closed contour K1 is sitting inside. D2 is the blue shaded region where your simple closed contour K2 is sitting inside. So now you have two simple connected region where K1 and K2 are two simple closed contours sitting inside. Okay, so therefore by Cauchy's theorem or Cauchy-Goursat theorem, integrations over K1 same as integration over K2 is equal to 0. Both contour integration will be 0. Then I have to just add it. So now if I add K1 plus K2, look, if I have K1, if I have K2, if I add it, you see L1 and minus L1 will get cancelled, minus L2, L2 get cancelled. What will remain is that C2 star plus C2 double star minus C1 star minus C1 double star. You can think about this is C2 star union C2 double star minus C1 star union C1 double star. But so what is C2 star and C2 double star? This is two parts of your contour C2. So if I take the union, I will get back my contour C2. Similarly, what is C1 star and what is C1 double star? It is two parts of your contour C1. So if I take the union, so I will have what is called the contour C1. So therefore, this union will give you the contour C2. This union C1 star union C1 double star will give you contour C1. Again, you just go back to the picture, it will be clear. Okay, for example, C1 star union C1 double star. So this is the portion C1 star, this is C1 double star, it will give you, the union will give you the full C1. Similarly, this portion is the C2 star and lower one is the C2 double star. So therefore, C2 star union C2 double star. So C1 star union C1 double star, which is C1, C2 star union C2 double star, which is exactly equal to C2. Okay, so if I do that one, so therefore it turns out that K1 plus K2 is exactly equal to C2 minus C1. Now integration over K1, integration over K2 is 0. Again by using the formula of line integral or contour integral, if I take the sum, then it is nothing but, so this is nothing but integrations over k1 fz dz plus integrations over k2 fz dz. Each of them is 0, so therefore sum is 0. So therefore this is 0. And what is k1 plus k2 or k1 union k2? This is nothing but integrations over c2 minus c1. Again, by the properties of what is called contour integrations, I can break into two parts, integration c2 plus integrations of minus c1, which is same as integration c2 minus of integration of c1, which is 0, which will implies integration c2 same as integration c1. And that is exactly this conclusions. Okay. So therefore, if I have a multiply connected domain, the process is called deformation of contour. That means if I have a multiply connected domain and if I take a larger contour C1 and in the interior of C1 if I take a smaller contour, that is sometimes it's called the deformation of your larger contour C1. If my functions f is analytic on the multiply connected domain and suppose both C1 and C2 are two simple closed contour sitting inside my domain D, then the line integral over C1 is exactly equal to line integral over C2. Okay. Now what is the advantage of that? Advantage is that if I want to calculate this kind of object. So I want to show that, okay, let C be a positively oriented simple closed contour enclosing the origin. Now show that this value is exactly equal to 2 pi using Cauchy-Goursat theorem for multiply connected domains. How will you do that? Okay. So therefore I want to calculate integration C dz by z. What is that value? Now then you can say that, sir, I can certainly use what is called definition of contour integrations, perfectly all right, you can use it. But the point is that, so look, what is C? C is positively oriented simple closed contour, that's it, nothing else. If I give you the parameterizations of C, then you can use the definitions, you can, because your integrand is 1 by z, so it's perfectly all right, you can calculate it. But you see the C is just a positively oriented simple closed contour, it could be anything. Suppose you have no idea about the parameterizations of that. If you know the parameterization, then you can use the definition of contour integrations and you can do that. But you do not know the parameterizations, because what kind of contour? It's just a simple positively oriented closed contour, that's it. Now look, so what is your integrand? F of z is equal to 1 by z. Now what kind of functions? This function is analytic everywhere except the point origin. That means your domain you can think about C minus 0. So f is analytic on C minus 0. F is analytic. Okay. So this is C minus 0. It's a multiply connected domain because if you have a complex plane except the origin, then there is a hole at the origin. So it's a multiply connected domain. What I am doing is that take any contour C which is positively oriented, any arbitrary contour, then I am saying that calculate this object. But this contour, you do not have any control on that because it would be just a positively oriented simple closed contour, that's it. You do not have any idea about the parameterizations. Now if you do not know the parameterizations, how you calculate that one? It is difficult, right? Now to prove or to get the calculations, you have to use, or you get the value of this what is called contour integrations, you have to apply what is called Cauchy-Goursat theorem for the multiply connected domains. So this is my origin. This is my simple closed contour positively oriented C, and I want to calculate this one. What I will do, even though I do not know anything about the parameterizations of my contour C, what I will do, interior to C, I can take a small circle that I can always have it, right? With some radius say epsilon, that I can do that, or say R. Very small, because you see you have a complex plane except the origin. Take any simple positively oriented closed contour, then in the interior you can always have a small circle of radius R and center 0. You can always have it, right? And suppose this is my circle CR. Now once we have a circle of center 0 radius R, you know the parameterization. What is that? The parameterization is that suppose CR is a circle of center 0 radius R. What is the parameterization? So parameterization is gamma of t r e to the power it and t runs from 0 to 2 pi. That parameterization you know. Now you see this is my C. So this is one simple closed contour, right? You can take a small circle CR of radius R which is also positively oriented. Now this simple closed contour, that means circle of radius R which is lies interior to C, right? And my function is analytic on a multiply connected domain C minus 0. Both contour C and CR are sitting inside. So therefore by deformation of contour, this is exactly same as integration CR dz by z. So the value of the contour integrations over C is same as the value of the contour integrations over CR. even though I do not know the parameterizations of C, but I do know the parameterizations of CR, then you apply your definitions of line integral. What is that, this value? Then you can easily calculate it because you know the parameterizations. What is that? This is integration 0 to 2 pi f of gamma t gamma prime t dt. F of gamma t means what? This should be 1 by z, right? So that way this should be 1 by gamma of t, then gamma prime t dt. What is that? This is 0 to 2 pi, 1 by gamma t is there, r e to the I t, then gamma prime t, that means r I e to the I t dt. So r get cancelled, e to the I t get cancelled. So this should be 0 to 2 pi I times dt, and this is nothing but 2 pi I, and that is exactly this one. Okay, so therefore the advantage of deformation of contour in a multiply connected domain to evaluate this kind of problem, one of the advantage. So for example, I have a function f of z is equal to 1 by z, which is analytic in a multiply connected domain C minus 0, and I am considering any simple closed contour around the origin, but I have no idea about the parameterizations. But I would like to calculate the corresponding contour integrations of these functions f of z is equal to 1 by z. How to do that? Take whatever simple closed contour around the origin, you can always have a small circle of radius r centered at origin. Then using the deformation of contour, integrations over C is same as integration over CR, and since you are dealing with a CR is a circle of radius r centered at origin, you can have the parameterization explicitly. Then use the definitions of contour integrations, you can calculate this kind of integration. That is one of the advantage of what is called deformation of contour. Okay. Once I have that one, then this is the corresponding theorem for Cauchy's theorem for multiply connected domain. Okay. So what is that? So I am just stating it. Okay, I am not going to prove it, but proof will be similar. Okay, what will be the statement? First, let me just go through the statement, then I'll explain how you prove it. So statement is the following. So suppose you have a multiply connected domain. Now this is your multiply connected domain. Multiply connected domain means what? So that means you have a domain and there is a hole, right? But in your multiply connected domain there could be many holes, right? Look this domain. So this is domain, so this is one hole, two hole, up to n many holes are there. So that is the white portion, it is not a part of the domain. Only the blue one, only the blue shaded region, it is the domain. I mean it is a domain, but there are finitely many holes. So this is a multiply connected domain, right? Now suppose C is a simple closed contour positively oriented. So this is the top contour C. Okay, this is a simple closed contour positively oriented. Now what I am doing, so you have finitely many holes, so what I am doing is just CK denotes the finite number of simple closed contours positively oriented such that the interior of C and whose interiors have no points in common. So what I am doing is that, so I am considering a contour C positively oriented in the bigger contour, then since it is multiply connected domain, so and there are finitely many holes, what I am doing is that each hole I am considering a small simple closed contour, so let it be C1, C2 and Cn. What are the properties of C1, C2, Cn? That means the interior region bounded by C1 and interior region bounded by C2, both intersection is phi. So that's what I have written. So all positively oriented and that are interior to C. Of course this should be interior to C. That means the region bounded by the simple closed contour C, C1, C2, Cn should also be lies in that region. Now look, the blue one is the region, this is the region which is bounded by my contour C, and look C1, C2, Cn, this is also in the blue shaded region, that means these are interior to C. So that's what I have written. So CK denotes the finite number of simple closed contour, all positively oriented, that means anti-clockwise directions, that are interior to C, that is also okay, whose interiors have no points common. Now this is the interior of C1, this is the interior of C2 and this is the interior of Cn, so there is no common point in the interior of Cn with interior of C2 up to interior of Cn. If this is the case, then what is my conclusions? So earlier, if I have only, suppose this is my domain and suppose there is only one hole, and if I take a contour, say this is my C1 or C2, and suppose there is a small contour, say C1, then integrations over C2 is same as integration over C1, right? Since there is only one hole. Now what I am doing is that if I have two holes are there, then it is also multiply connected. Now suppose if I take a contour C in the bigger one, and suppose if I take a small contour around the one hole, this is say C1, and suppose another contour C2 with another hole C2, and suppose this is the bigger one C3, then the conclusion is that integrations over C3, which is same as integrations over C1 plus integration over C2. Since there are two holes are there, so therefore the corresponding C1 and C2 are two simple closed curve around this hole. So therefore the integrations over the larger contour, it should be sum of each contour Ck's. So that is the corresponding theorem. So if I have a C is a simple closed contour positively oriented, Ck denotes the finite number of simple closed contours, all are positively oriented, that are interior to C, whose interiors have no points common. If my function is analytic throughout the closed region consisting of all points within and on C, of course this is the blue shaded region where my function is analytic, except for the points interior to each Ck. Now interior to each Ck, this is the white region. Interior of C1 is the white, interior of C2 is the white, interior of Cn is the white region. So these are the white one is not a part of the domain. I mean there are holes. So therefore it should not be analytic because my function is not even defined there. So my function is analytic only on the blue shaded region. I have a contour, the bigger contour C, which is lies inside the blue region, and interior to that region, interior to the domain bounded by my simple closed contour C, I have n many simple closed contours C1, C2, Cn, whose interior of each Ci's the intersection is phi. Of course interior of each Ci's, they are not part of the domain. If these things happen, then the value of the contour integrations of the larger contour C over C, that is this one, is same as the sum of the contour integrations of C1 plus C2 up to Cn. So earlier one I will have only one hole, so therefore the corresponding deformation of contour says that integrations over C2 is same as integration over C1. But now if I have a domain and if I have a, like say two holes are there, it is also multiply connected, and if I take a bigger contour C and if I take a small contour C1 and C2, this is C2 and this is C1. C1 and C2 should be interior to the domain bounded by C. Their interior of C1, intersection interior of C2 should be phi. My function should be analytic on this multiply connected domain. Then integrations over C, which is same as integration over C1 plus integration over C2. So that's the statement. So this is the corresponding Cauchy's theorem for multiply connected domain. So therefore, if I have a multiply connected domain, say finitely many holes are there, and if my function is analytic, and if I take a simple closed contour, the larger contour sitting inside my domain D, along with I have finitely many holes, means if I take finitely many simple closed contour around each hole, then the value of the contour integrations over the larger contour same as the sum of the contour integrations over the smaller contour. But you have to be very careful. It should satisfy all the hypotheses of the theorem. That means C1, C2, Cn, the smaller contour that you surrounded around each hole, this should be in the interior domain bounded by the larger contour. It should be like that. That means in my picture, that means the blue shaded region where my contour C is, along with C1, C2, Cn, that is also lies in the blue shaded region, that are also interior to the domain bounded by C. If this thing satisfies, along with the fact that my function f is analytic on multiply connected domain, then I can write integrations over Cf is sum of integrations over Ck. So this is the corresponding Cauchy's theorem for multiply connected domain. Okay, so I think okay, so therefore what we have learned. So earlier we have learned like Cauchy's theorem for simply connected domain. For the multiply connected domain, the statement is that first we have learned the deformation of contour, and then if I have a domain which have finitely many holes, then this is the corresponding statement of Cauchy's theorem for multiply connected domain. Advantage, as I said, so if I take a multiply connected domain and if I want to calculate some, say, contour integrations or line integral, then of course, so like if I give some kind of simple closed contour, there you do not have any idea about the parameterizations, but by deformation of contour, if you somehow realize that yes, your domain is multiply connected domain, and you have a kind of simple closed contour that in that contour you do not have any idea about the parameterizations, but by deformation of contour I can bring it to a known contour where you know the parameterizations, and there I can evaluate my what is called contour integrations, or contour integrations I can do that, okay, by using the formula. So now I come to what is called Cauchy's integral formula. Again, like Cauchy's theorem or Cauchy-Goursat theorem, that is also one of the fundamental theorem in what is called complex analysis. So what is Cauchy's integral formula? Cauchy's integral formula, if I say in one line, suppose I have a function f and suppose I have a domain D which is simply connected, and if I take a simple closed contour sitting inside my domain D, and I am considering a point which is interior to the, or I am considering a point which is lies interior to the domain bounded by simple closed contour C, then what is Cauchy's integral formula says is that I can have the value of my functions at that point if I know the value of the functions on the contour. So that's what I have written. So the following theorem shows that the values of an analytic function f interior to a simple closed contour C are completely determined by the values of f on the contour. So that means it says that if I have a functions, if I have a simply connected domain, so that's the picture. So if I have, this is my domain D which is simply connected. If I take a contour C, simple closed contour sitting inside D, and if I take some point Z0 which is interior to C, that means the interior region bounded by C, in that domain if I consider a point Z0, then Cauchy's integral formula says that I can calculate, or the value of the functions at the point Z0, I can calculate that value if I know the value of my functions on the contour. So that's exactly I have written. So values of an analytic functions f in the interior to a simple closed contour C are completely determined by the values of f on C. So therefore, if I know the value of f on the contour C, then whatever point I can take interior to C, I can have the value of the functions at the point Z0 by this formula. That's what it says. So it says that, okay, this is the statement. It says that let f be analytic in a simply connected domain. This is my domain D. Let C be a simple closed positively oriented contour. This is my contour C, which is lies entirely in D, because the portion C, just looking at the gray region, C is entirely lies in D. If Z0 a point lies interior to C, interior to C means the domain bounded by C, which is a domain interior, interior means the interior part of that domain. So that means this is the domain. So that means the domain bounded by your simple closed contour. If I take a point on that, or interior means you should not consider the point on C, but you should consider the point inside C, that is called interior to C. Okay, so whatever point I can take Z0 interior to C, then I can have the value of the functions at that point if I know the value of the functions on the what is called contour. So that's what it is. So look at the right hand side. So right hand side, I am, if I evaluate this what is called line integral or contour integrations, then I can have the value of my functions at the point Z0. So what is that? So f of Z0 should be exactly equal to 1 by twice pi I contour integrations over the contour C, but what will be my integrand? Integrand is fz divided by z minus z0 dz. So that means this is, you can say that this is 1 by twice pi I integration C gz dz. What is my gz? My gz is fz divided by z minus z0. So therefore, if I evaluate, or if I get the, if I calculate the contour integrations of G, then I will have the value of my functions f at the point Z0. In other words, what is your G? This is f divided by z minus z0. Now this is a known function, 1 by z minus z0, right? But if I know my functions f, fz, now what I am doing, I am just calculating this what is called contour integrations. That means if I know my value of the functions f of z, where z running over C, that means you do not need to know the value of the functions on each part of the domain. So even if I know my value of the functions on my contour, then I can calculate my value of the functions at the interior. So that's what it says. The following theorem shows that the values of an analytic function f interior to a simple closed contour C are completely determined by the values of f on C. Okay, so this integrations, if I calculate, so you just need the value of the functions on C, because this function is well known. And if I calculate this contour integrations, the value will be exactly equal to the value of the functions at Z0. Now from this is for maybe next class I will prove the I will give a proof of Cauchy's integral formula. But just looking at the kind of statement or the formula, you can easily guess what I will do next. Because you see, finally I have to do this, or I have to calculate this line integral or contour integral. integration C of gz dz. And what is my gz? My gz is f of z divided by z minus z naught. Correct? Now what is f? F is analytic in my domain, that is perfectly all right. But what about the denominator 1 by z minus z naught? Because 1 by z minus z naught, that will have some kind of difficulties at the point z naught, right? So at the point z naught, this function 1 by z minus z naught, which is not analytic because there will be singularity at the point z naught, except z naught my function is analytic, then I can say that my function g is analytic. But my function, I cannot say that my function g is analytic on the domain D, because at the point z naught the denominator will have a problem. So therefore I cannot say that my function g is analytic on whole D, but I can say that my function g is analytic on a domain D minus z naught. So that means I have a domain D. If I take out the point z naught, that means if I take out the point z naught, there my function g is analytic. So that means then even if my functions f is given in a simply connected domain, but if I consider the function g, which is f divided by z minus z naught, this function is analytic on a multiply connected domain. That means I have a domain D and then I am taking out the point z naught. That means there is a hole at the point z naught. So now I have a function g which is analytic on a multiply connected domain, and I want to evaluate or I want to calculate the contour integrations over some contour, simple closed contour around the point z naught. But just now I said, so since I have a functions analytic on a multiply connected domain, then I have to use what is called Cauchy's theorem for multiply connected domain or deformation of contour. Now if I use deformation of contour, then I will say that, well, my function g which is analytic in a multiply connected domain, and what is my domain? My domain is D minus Z naught. That means there is a hole at the point Z naught. So what I will do, I want to calculate contour integrations of G over this contour C. By deformation of contour, what I will do, I will take a very small circle around the point Z naught, and for that circle around the point Z naught, I know the parameterizations even if I do not know the parameterizations of C. So therefore, by deformation of contour, this contour integration, it is exactly equal to same as CR comma Z naught G of Z dz. Okay, what is CR comma Z naught? CR comma Z naught is a circle at the center at the point Z naught and radius R. Then by deformation of contour, the contour integrations over C is same as the contour integrations over CRZ naught, because CRZ naught is a small circle positively oriented around the point Z naught, but CRZ naught, since it is a circle, I know the parameterizations. What is the parameterizations? Gamma of t should be Z naught plus R e to the IT, t runs from 0 to 2 pi. And then just use the definition of contour integrations, because I know my function g explicitly. What is g? F divided by z minus z naught. F is given. If I use the formula, then I will conclude that yes, your f value of the functions f at the point z naught, which is exactly equal to 1 by twice pi I, contour integrations of fz divided by z minus z naught dz. So that's the idea is this one. You have to use deformation of contour, and then of course you have to use the what is called analyticity of f or continuity of f to conclude that f of z naught is exactly equal to 1 by twice pi I integration c fz divided by z minus z naught dz. So maybe that part I will, in my next lecture I will do that, but that's how the idea, and that will give you, and this formula is known as what is called Cauchy's integral formula. Okay, so Cauchy's integral formula, if I say one line, I can evaluate my value of the functions interior to a simple closed contour if I know the value of my functions on the contour. So that's what it says. Okay, so in my next class I will talk about the proof of Cauchy's integral formula using deformation of contour. The idea I have already discussed. I think I should stop here. In my next lecture I will start with the proof of Cauchy's integral formula. Thank you.